Good afternoon, everyone. Hope you had a good Thanksgiving break. So we're going to start a new unit today on principal component analysis. So let me talk a little bit about the motivation of principal component analysis, which is dimensionality reduction. So the idea here is that many modern data sets have a high dimensionality. D, that's the number of features, is large. And we'd like to reduce that dimension if possible for various reasons. You know, maybe one thing we might be doing is using those features to do some sort of classification or regression, and maybe by reducing the number of features, we can make this task simpler. Or maybe we just want to save memory or storage space. We don't want to store all the features. Or maybe we want to reduce them all the way down to 3 or 2 dimensions so that we can actually visualize what's happening with the data, which is something we can't do when it's in high dimensions. So there are various reasons why we might want to reduce the number of features, and different from the feature selection that we talked about back in Unit 4, where we're taking a few features and ignoring the rest. Here what we're doing is we're going to be doing sort of a transformation of all the features to reduce them to a smaller space. So we'll talk about that in just a moment. But that's going to be the focus of this unit, is dimensionality reduction via PCA, principal components analysis. We'll also talk about, towards the end, another sort of modern tool for visualizing high-dimensional data sets called TSNE, which is good to know about and something you could use for your projects if you like. Okay, so just to start at the beginning, in this unit, different from all our other units, we're focusing on a data set that has no labels. It just has feature vectors. So as always, we have n samples in our data set, and each of our samples xi has d features like always, but as you notice, there's no y's, there's no targets or labels. So, and this could be for a couple of reasons. Maybe there are targets or labels, but we're just going to ignore them for now. We're going to focus on the features alone. Or maybe there are no labels at all. So this sort of problem where you're focusing on features without labels is known as unsupervised learning. And it's different from what we've considered until now in the class, which is supervised learning. Supervised learning includes things like regression classification. Unsupervised learning includes things like dimensionality reduction and clustering, which we'll talk about in the next unit. So again, the motivation is we'd like to reduce the dimensionality D. One other thing we can do is we can, just like always, we can stack our samples into the rows of a matrix X. So this is the same way we've constructed X before. So now our data set is represented by a single matrix. One thing to note in this unit, for simplicity, we will assume that our data has been centered. In other words, the mean has been removed, so that if you sum all of our samples, you get 0, or you could say the sample mean is 0. Okay, so that's something easy to do. We can do that with any data set, and we'll just assume that's been done. Okay, so a little bit about the motivation. We're going to be using face data in this as the demo in this unit, and the face data we're using is an older data set called labeled faces in the wild. And these are actually relatively small pictures of faces. They are 50 by 37 only, so as images go, those are really small. Similar to MNIST in size. So that means a total of 1,850 pixels per image. And so you could say that this is high dimensional, or you could say it's not that high dimensional. But basically there's 1,850 numbers representing each face, and the question is, do we need to represent the face with that many numbers, or can we get away with using a much smaller number of values to represent each face without losing much quality? And as you'll see, Just with PCA, which is a relatively primitive technique, we can reduce this to about 300 numbers from 1,850, so we can compress by about a factor of 6 without really seeing much difference in the quality. There's definitely much more sophisticated ways to do compression, but this is just one example. And then we can also see, this is sort of going to be the data set we're working with. All right, so just a little bit more about the data set. So this data set in total contains 13,000 images. The images look kind of like these. These are just 4 examples. And the data set has an image, and it does have a label. It has the label of the person who's being shown in that image. We're going to ignore the labels for most of this unit. We're going to, again, focus on just the features alone, but the labels are there. And so if we wanted to, at the end, we could, for example, do PCA to compress the features and then see how well it works for classification, compare it to classification done with non-compressed features to see if we've lost much. So that's something we can do because we do have the labels. But again, I just want to emphasize most of what we're talking about in this unit is not about labels, it's just about the features alone. And we're going to work with a subset of 1,288 images, and the way we're constructing that subset is when we load the data, we're insisting that there's at least 70 faces per person, and then when you do that, there's only 7 people in the data set who have 70 or more faces, and then if you, there's 70 more samples. If you basically aggregate all those samples, you get 1,288 total. Okay, so all right, so let's get into the ideas behind PCA. So most of today's lecture will be a lot of math, a lot of linear algebra. To explain what PCA is, we'll derive it, and then next unit we'll focus much more on the application, show a lot of pictures, show a lot of stuff based on the data set. But today, unfortunately, is just a lot of linear algebra. So let's just start, before we get into a lot of linear algebra, let's start with just the main ideas. What is PCA doing exactly? So there's basically 2 main ideas. The first main idea is that we are going to be doing a linear approximation of every feature vector xi. And what we mean by that is we are going to do it this way. We're saying xi, the ith feature vector, ith sample in our data set, is approximately equal to some matrix B, which it does not depend on I. This is going to be a fixed matrix for the whole data set, times we can call this a code vector, this zi, and zi is going to have fewer elements in it than xi. So let me draw a little picture. So this vector xi is approximately equal to a matrix, a tall matrix times a shorter vector. Okay, so this vector xi has D features, but this matrix zi has capital R features. And in most cases, we are hoping that R is much less than D. Okay, so hopefully from this, you can see the compression going on. Let me just finish. So this is like B, this is Zi. So what we'll have to do is we'll have to figure out how to design B and Zi for all the I. But once we do, you can see that on one hand, I could have a data set of samples xi, where I goes from 1 to n, or if we want to use PCA, we could have B and the vector zi, where I goes from 1 to n. And if you have a lot of samples, the extra cost of storing this matrix B, which is like your dictionary, is not very large. But there's way more values in that set than there are in this set, because each of these has dimension D, whereas these have dimension R being much less than D. And so overall, by working with this representation, you save a lot of storage, over working with this representation. Okay, so that's the first main idea. We're doing a compression, and this is basically a linear compression. You can say that you can reconstruct an approximation of all the xi's by taking your B matrix and multiplying it by the corresponding zi. And this should give us an approximation of xi. Okay. So is that idea kind of clear? So we're representing each of these approximately by matrix B times a short vector zi. And it's up to us to choose R. R is a design parameter. Intuitively, the smaller that R gets, the worse the approximation gets. You can go all the way down to R equals 1. If it's R equals 1, then all of your xi's are going to be basically one constant vector times some scaling. Probably that's not going to be a very good result, right? But so usually we don't choose R equals 1, but you choose some R that's large enough that this is a decent approximation. At the other extreme, if you choose R equals D, then one choice is just to choose the identity matrix here, and then you're doing no compression at all. So that would be kind of silly too, because the whole point is to do some amount of compression. So generally speaking, R is going to be a number that hopefully is much smaller than the original feature dimension D, but is large enough that we get a good approximation. Okay, so that's the first main idea. The second main idea is, well, how do we design the B and the ZIs? And we design them to minimize RSS. So we want to choose B and all the different ZI vectors so that when you look at the sum over all our data samples of the difference between the original feature vector xi and its approximation, that this is the RSS, that RSS is small. Right? So that's pretty intuitive, objective. You could imagine coming up with other criteria for which to design B and ZI, but this one, based on a sum and squared Euclidean norm and all that, is relatively easy to work with. Basically, we can derive, as we'll see, we can derive the optimal B matrix and the optimal ZI vectors in closed form. With other criteria, like if you replace this with an L1 norm, you wouldn't be able to do that in closed form. Or if you used, if you replace this with a much more complicated function that takes you from ZI to XI, like you could replace this with a neural network. People do that, but we can no longer do this nice derivation. We can't get anything in closed form. So this is pretty simple idea, about as simple as you can get for approximation. And this is about as simple as you can get for a design objective. But together, they give us something that's useful, and it's very well known. It's a very classical idea. So that's why it's taught in a lot of machine learning courses. Okay, so basically you put these two together and you get what we call principal components analysis. So any questions on the setup? Okay, so one thing I should warn you that PCA is, you could say it's a lossy compression. So you're losing information. When you do this, generally speaking, the performance of some downstream processing of you're replacing the true features with these approximations. If you then use these approximations downstream, you can expect things to get worse. So for example, if we're doing PCA to compress our features and then we use our features to do something like classification, you can expect that the classification will be worse. Maybe not much worse, but it should be a little bit worse. But there's another issue, is that when you think about the downstream task and when you think about how the compression is done here, there may be a mismatch. So here we're saying, come up with an approximation that is close to the original features in the L2 norm. While that sounds good, and it's maybe a good thing to do, in many cases, it's not always a great thing to do, especially if you're doing classification. It could be that when you're doing classification, the things that you really need to distinguish which class your xi comes from might actually be thrown away in this criteria. Maybe this is focusing on things about xi that are useful for approximating xi, but not useful for classification. So there could be a mismatch between this particular design that PCA uses and the task downstream, so you just have to keep that in mind. All right, any questions about the high-level ideas? Okay. So I'll first tell you what the solution is, and then we'll go through a proof. So it turns out that the optimal dictionary, this is the B matrix, the optimal dictionary here, is constructed as follows. First, you compute the sample covariance matrix of your features. Now, when you look at this, you might say, well, isn't the covariance defined by first subtracting the mean and then taking the outer product? Yes, but remember that our data has already been centered. We already subtracted the mean, and so that's why we can write the covariance like this. Okay, so this is something we talked about. This matrix, it showed up back in units 1 and 2. So this is something we've seen before. What's new here is if we take an eigenvalue decomposition of this matrix, Q, we can write it in terms of its eigenvectors, which are these VJs, and its eigenvalues, lambda j. We'll be talking a little bit more about eigenvalue decomposition later, but if we write it this way, then to construct the optimal dictionary, what you do is you sort these eigenvectors and eigenvalues. You sort them so that the eigenvalues go from biggest to smallest, and then you take the eigenvectors corresponding to the largest R eigenvalues, you stack them column-wise into a matrix, and that gives you the optimum dictionary. And then the other thing you do is you take that same matrix, we'll call it capital VR, you take that matrix, transpose feature vector xi, and that gives you your optimum code vector zi here. Okay, so basically that's the solution in a nutshell. It's not yet clear why this is a solution. That's what we're going to derive later, but this is basically how PCA is done. And so here's some visuals. On the left here, we have a case where our original data, original features are three-dimensional, so we can plot them and we can visualize them in 3 dimensions. And we are approximating them using 2-dimensional code vectors. So essentially what we're doing is we're finding the plane that best fits the data, in the sense that the differences between our data samples, or the distances from the data samples to the plane, the sum squared of those errors should be minimal. So that's essentially what we're doing. This is if the PCA is using 2 dimensions for its approximation. If it's using just 1 dimension for its approximation, then we're finding the best line, in the sense that if you measure the distance between all the samples in that line, the sum squared distances are minimal. So that's essentially what PCA is doing. It's coming up with a subspace that best fits the data. And these are different eigenvectors or directions are known as the principal components of the data set. So in this case, these directions, the directions that are defining this plane, those are the principal components. And in this case, there's just one principal component. It's the direction that's defined in that line. Okay, so that's the solution. So let's see if we can derive this from first principles. So The derivation goes in 2 steps. The first step is really easy. The second step, not as easy. But the 2 steps are, first we're gonna fix the dictionary B, it can be anything, and we'll find the optimal coefficients for an arbitrary fixed dictionary. And second, once the coefficients are determined, there'll be a function of B, plug that in and solve for the optimal dictionary B. Okay, so the first step, like I said, is really easy. It looks like this. So if you remember, this is what we're working on here. So if I want to find the optimal Z1, I can just forget about this entire sum. I just look at the optimal, I look at the first term in the sum, and I would just have x1, z1, and I can just work on this norm. And we can do that for any I, so that's where we get this problem. Okay. So when you look at this, this is a least squares problem, just like the ones you saw back in units 1 and 2. And we derived the solution to that. At the time, the notation was different. I think we had A and beta, but everything else is the same except for a change in notation. And we know that the solution here, the zi that minimizes this squared 2 norm, takes this form. Okay. So for any matrix B that we choose, this is going to be the optimal zi hat, or the optimal zi. So we can take this zi and we can plug it back into here. And now we don't have to worry about optimization over Z, we just worry about optimization over B. So that is what we have here. So this is what we plugged in for ZI. And now you can see we have an optimization problem that involves this unknown quantity B and our data values xi. So some of you may have seen matrices that look like this before. This is known as a projection matrix. And we can also rewrite this by putting an identity here, because identity times xi is this xi. And then this is another projection matrix. This is actually known as the orthogonal projection matrix or projection operator. And let's talk a little bit about that on the next page. Okay, so this page is all about the idea of projection. So first we have to talk about a subspace. So a subspace, you can think of it, let's say we're working in 3 dimensions, which is what's shown in this picture. A subspace of 3 dimensions would be a 2-dimensional plane, as shown here, or maybe a 1-dimensional line. Those are both subspaces of this 3 dimensions. Mathematically, the way that we define a subspace is we need 2 vectors that from which, with linear combinations of those 2 vectors, we can construct any vector in the plane. So if we put those 2 vectors, stack them column-wise into a matrix B, we say that the column space of that matrix B is the set of all vectors BZ, which you can think of as what the Z is doing is just doing a linear combination of the columns of B. Right? So this is basically saying the column space of B is just the set of all linear combinations of the columns of B. So B would be defined by any 2 vectors that are sitting in this plane and that are linearly independent. From those, you can construct, with a linear combination of them, any other vector in this plane. Okay, so this is the column space of B. That's what the plane is. So when we talk about the orthogonal projection of X onto that column space, it's a pretty intuitive idea. It's sort of like here you can see X is a vector in 3D. It's not necessarily in the plane. And orthogonal projection is just saying what is the closest point to X that lies in the plane. So one way to do that, if you imagine that there's a flashlight shining down from above, the projection would just be the shadow down here This is our x hat, the optimal projection of x in that plane. It's optimal in the sense that the distance between x and the approximation, which we can call e, the norm of e is minimized. Okay, so any other x, you can imagine, like I could construct an x here that's going to have a larger distance, a larger error than this one. Okay, so here we're writing x as the approximation x hat and this error, but we want the error to be as short as possible, norm as small as possible. And what we do to do that, we find the error that is perpendicular to the column space. We need this to be at a right angle. Okay, so I think these are things that you've probably seen many times before in previous classes. So the way you do this in terms of linear algebra is if you're given x and you want to know what is x hat, the projection, you can construct this projection matrix or projection operator using this matrix B as follows. B times B transpose B inverse times B transpose. So here we're assuming that this matrix is invertible, which means that the columns of B are linearly independent. Okay, so that's how you get this matrix PB, and if you multiply x by PB, you get this approximation x hat that lives in the plane. And if you want to get its error, this is called the orthogonal complement, then you multiply x by PB perp, which is just I minus PB. Okay, so these are the orthogonal projection operators. So I'm curious, how many of you guys have seen these things before? Okay, a few of you guys have. Okay, good. So there's two really important properties of a orthogonal projection operator. In fact, there's only two properties you need to define them. They're symmetric and they're idempotent. Okay, so what does symmetric mean? It just means that if you take the matrix and you transpose it, it's the same thing. And idempotent means if you square the matrix, it's just the same as the original matrix. It's a little bit easier to understand the idempotency idea if you think of PB as an operation that you apply to a vector. It's, the multiplication by PB, if you think of that as an operation, then multiplication by PB squared is like doing multiplication by PB twice in a row. And for a projection operator, the way it works is for any vector x, it projects it into the plane. But once you're in the plane and you do another projection, nothing changes, right? Because you're already in the plane. So that's why when you apply the projection operator twice, it's the same thing as applying it once. Okay, so when you have these two properties, symmetry and idempotence, that is the definition of an orthogonal projection operator, which is this guy. And it turns out that both of them are symmetric and idempotent. Okay. Another important thing about these operators is that when you look at their eigendecompositions, they both have eigenvalues that are either equal to 1 or equal to 0, but never anything else. And in this case, because our B matrix has R columns, it turns out that the projection matrix has R eigenvalues that equal 1 and all the rest equal 0, while as the PB perp matrix has R eigenvalues that equal 0 and all the other ones equal 1. Okay, so we're going to use all these properties going forward in our derivation. Okay, so now that we see this, we can understand a little bit more about the PCA, what PCA is doing. So if you come back to this page here, you can see that B hat is the B that minimizes this. So this is the sum across our data set. This norm squared is measuring the norm squared of the xi times this orthogonal projection operator. So essentially, when we multiply xi times this gives us the error, the projection error. So in other words, so here we've just rewritten this a little more concisely. This is how we're trying to solve for B. And you can see that this quantity is just this vector is just the vector that comes out orthogonal from this plane to the data sample xi. Okay, so these are all the error vectors. And we're just saying we want the sum of the squared norms of them to be minimized. So B defines where the plane, how it's tilted, where it lives. We just keep moving that around until all these projection errors the sum of the squared projection errors are as small as possible. So that's what PCA is doing. It's actually kind of intuitive. So let me just highlight that. So PCA chooses B to minimize the sum squared projection error. That's basically what it's doing. So now the rest of what we have to do is try to relate this B to that eigenvector matrix. So that takes a little bit more work. But we get to use a number of the tools that we've seen so far in the course. Again, reinforce them a bit. So here's the cost. We're going to call this thing, call it JB. It's the cost on our choice of B. And the first thing we can do is we can use the fact that when we have the norm of a vector squared, that's the same thing as that vector transpose times that vector. So we're just expanding the norm, writing it in terms of transposes. And next step is we realize that if PB perp is a projection matrix, that this transpose doesn't do anything. So because it's a symmetric matrix, so you can imagine getting rid of the transpose. At which point you have PB perp squared, but we said orthogonal projection matrix. We know that PB perp squared is the same as PB, so we're back to here. So we simplified things a little bit. Next step is to realize that this is a scalar quantity because we have a row vector times a matrix times a column vector. So this is just a scalar. And so I can always apply the trace to a scalar. The trace is the sum of the diagonal elements of a matrix. And if it's a scalar, the trace of the scalar is the same as the scalar itself. So we're just applying the trace to the scalar. But the reason trace is often used in derivations is it allows you to use this trick down here, which says the trace of a product of matrices is the same as the trace where you reverse the order of the matrices in the product. So as we know in linear algebra, AC is not equal to CA in general, but when it's inside a trace, the trace becomes equal. So the reason we're doing this is now when we have the trace of this, we can actually move the xi, actually we're going to move this xi transpose to the back. So we have this, and now you can see we have a matrix times a column vector times a row vector. So this whole thing is a matrix, right? But that matrix has the sum of the diagonal elements of that matrix is the same as this number, or the sum of the diagonal elements in this little scalar matrix. Okay, and the reason we did this is the trace is a linear operation, which means we can move the sum through it. In fact, we can move the sum through this multiplication by PB perp, and now the sum is sitting right in front of our xi transpose, and we can also sneak in a 1 over n there if we put an n on the outside, and all of a sudden we see that this is our covariance matrix, Q. Okay, so we've finally written this cost here in terms of the covariance matrix Q and this orthogonal projection matrix. Okay, so we're getting a little closer. So the next thing is to talk a little bit more about sample covariance matrices. They have some very important properties. Okay, the first important property of a sample covariance matrix is that it's a positive semi-definite matrix. So what we mean by a positive semi-definite matrix, it's a matrix Q such that for any vectors x that you can dream up, x transpose Q times x is always non-negative. There's no way to get that to be negative. And we can do a short proof of why this is, why any sample covariance matrix must be positive semi-definite. So we start with our quadratic form. We plug in Q for our sample covariance matrix. We exploit linearity to move this stuff to the front. And then you can see we have the sum of a product of two scalar terms. This, again, this is a row times column. And if you look at these two terms, they're actually the same. Because they're scalars, you can transpose them, it doesn't change. And if I transpose this one, if I transpose this whole thing, we know that essentially it will swap the order of these, at which point it looks like identical to that. So now you can see that this is really the same thing as this, so we can just write it as this squared. And finally, you can see that the average of any non-negative, being squared, they must be non-negative. Average of non-negative quantities must be non-negative. So, so finally we get the proof of this sample covariance matrix being positive semi-definite. Okay, so now the reason we care about that is if you have a positive semi-definite matrix, then the eigendecomposition has a very particular form. You can write it as a matrix V times a matrix lambda that's diagonal times a matrix, the same matrix V transpose. And V is a special matrix. It's an orthogonal matrix, meaning all of its rows are orthogonal to each other in unit norm. Also, all of its columns are orthogonal to each other in unit norm. So in terms of linear algebra, that means that if you multiply V times V transpose, you get identity, or if you multiply V transpose times V, you get identity. And here, I'm just writing the sub D to remind us that this is a D by D identity matrix. That's because this V matrix is a D by D matrix. Because Q is also a D by D matrix. All of these are. And this lambda is a diagonal matrix, and the values along the diagonal are known as the eigenvalues. The columns of V are known as the eigenvectors. And another important property of these eigenvalues that you get with positive semi-definite matrices is that the eigenvalues are non-negative and, yeah, real. So these are all important properties of Q, and this decomposition is also going to be useful to us. And this is, in fact, where we get this notion of constructing this B matrix using the R principal eigenvectors, which are the eigenvectors corresponding to the largest eigenvalues. So this is a theorem called the Eckert-Young theorem. Okay, we'll be back in a second. This is a theorem from a long time ago, but basically it says, this is sort of what we're trying to show. We've written our cost in terms of this N transpose PB perp Q, and this is saying if you want to minimize this by choosing B, you should choose B as the a matrix constructed from the R principal eigenvectors of Q. And to be technical, you don't need to choose only that B. You can choose any B for which the column space is the column space of VR. But certainly this one works, and this is the one we'll focus on. Okay, so the last stage of the proof is to convince you that this is true. So here's a relatively simple proof of Eckert-Young. So again, this is our objective. We want to minimize this guy by choosing B. And we can plug in the definition of this PB perp as I minus PB. And then we can expand this. We have I times Q minus PB times Q, which gives us two terms. And since we're optimizing this over B, we don't really have to worry about this first term. Because of the negative sign, if we want to minimize this, we just want to maximize this part. So let's define that as a utility, not a loss, but a utility. Somebody want to maximize. Define this as the trace of PB times Q. So now we can plug in our eigenvalue decomposition like this. We can exploit the trace property to bring V transpose to the front. And now when you look at this closely, you can see that you have a product of a matrix that's in general not a diagonal matrix times a diagonal matrix. But what you're doing eventually is you're taking the trace. You're taking the sum of the diagonal components. So all that's going to matter for us are what is on the diagonal of this matrix. Because all the off-diagonal elements of this matrix here will be killed when we take the trace. We just care about what's on the diagonal, and then those guys are going to be multiplied element-wise by these lambdas. So let's define alpha j, or let's define alpha j as the jth diagonal element of this matrix here. And if we do that, then this trace is just going to be the sum, as you go down the diagonal, sum of alpha j times lambda j. So these are the lambda j's here, and these are the alpha j's there. Okay. So as you can see, we're making our objective simpler and simpler. So now we want to maximize this. This is just this, you could say it's an inner product between an alpha vector and a lambda vector. But there's a few other things that we can use to solve this problem. The first is that we know that our alphas are guaranteed to be between 0 and 1. So this comes from something called the Rayleigh quotient. Basically, because V has unit norm, when you create this quadratic form, you will never get something smaller than the smallest eigenvalue in PB, nor will you get something larger than the largest eigenvalue in PB. And as we saw below, those eigenvalues are 0 and 1. So these alpha j's are going to live in the closed interval between 0 and 1. And there's one other interesting thing we can notice about the sum of the alpha j's. So the sum of the alpha j's, just by definition, that would be the trace of this matrix, which we use to define the alpha j's. And being the trace again, we can play this trick where we move the V to the left. And now, because this is an orthogonal matrix, this equals identity. So that vanishes. And so now you can see that this sum is just the trace of PB. But we can figure that out too. So we can plug in our expression for PB, which is B times this B inverse times B transpose. Again, play with our trace trick, move this to the front. And now you see we have a matrix times itself inverse. And so these will cancel and become the identity. But it's important to remember that this is an R by R matrix. So here we have an R-dimensional identity. And if I take the trace of this R-dimensional identity matrix, we just get R. Okay, so finally, we've boiled down our problem to this. So we want to find some coefficients alpha that live between 0 and 1. If you sum them up, you get R. And overall, we want to maximize this. So if you think about this in the right way, this is a simple problem that, as humans, you solve every time you go to a store and buy something. So it goes like this. Think of these alpha j's as a purchasing variable. Basically, if alpha j is 0, and j is going to index some items that are at the store. So if alpha j is 0, that means you buy none of the jth item. If alpha j is 1, that means you buy 1 unit of the jth item. So your objective is to choose how much of each unit you buy. You have to buy a total of R units. So when you sum all your alpha j's, it has to sum up to R. So total of R units. And you want to maximize this. You can think about this as how happy you are. So lambda j tells how much you like the jth item. And of course, alpha j lambda j is how much that you like the purchase. Because if you hate the item but you didn't purchase any, that's not a problem. And if you purchase a lot of an item that you like, you're going to be very happy. So this is sort of like your happiness. This is like your budget. And this is just constraints that you can't buy less than 0 or more than 1 of an item. And if you think about this, it has a simple solution. You have to buy between 0 and 1 units of each item, R units total. The most rewarding purchase is going to be 1 unit of your R favorite items. That's it, right? If you sacrificed and you bought any less than 1 unit each of those items, you would have to spend it on an item you like less. You'd be less happy. So you just want to figure out your R favorite items and buy 1 of each, and that's as happy as you can be. So at the end of the day, the solution to this is alpha j equals 1 if j equals 1 to R, or 0 if j is larger. So again, j is indexing the items, and we've sorted our eigenvalues from largest to smallest, which means the first R values of j are the ones we like the most. Okay, so basically, we now know how we want to arrange our alpha j's. We want the first R of them to be 1, the rest to be 0. And the way we can do that is by selecting B, as we said before. Because when we select B this way from those eigenvectors, turns out that, let's see, we can plug that in to here, and you get, we have VR, let me see, VR transpose, VR inverse, VR transpose. But remember that this VR is a tall matrix whose columns are orthogonal to each other. So that means this VR transpose VR is identity. And so that disappears. So this is just going to be VR, VR transpose. And now you can see that if you plug this into this expression, whenever j is between 1 and R, when you multiply this on the right by vj, you get a vector where the jth element is 1 and all the other elements are 0. And you're doing that on the right and left. And when you multiply those together, you just get a 1 if j is in that range, or 0 otherwise. So finally, we know what our alphas are, and we know how they're defined. This is just the definition from before. And we can see that if we choose B in this way, we're guaranteed to get the solution we want. Okay, so that's basically the proof. Just to summarize what we did now, we are given some centered data. So we've subtracted the mean. And each of our data samples, xi, we are going to approximate it as x hat I. And we're going to construct x hat by this dictionary matrix VR, where VR contains our principal eigenvectors, our sample covariance matrix. And we have our z hat I vector, which we construct by taking VR transpose times xi. So this is basically how we can get our approximation. And this is principal components. And again, it's basically projecting xi onto the subspace spanned by the R principal components of Q. So trying to minimize these sum squared distances here to find the plane that minimizes that. Or if you chose R equals 1, it's finding the line. Okay, so that's, let's see, I guess we can pause here for questions. Are there any questions on anything we've done? Realize it's a lot of linear algebra, a lot of steps. But if you go through on your own time, I'm sure you guys can follow all the steps. Nothing in there that you really haven't seen before. Just one last slide about how do we know how well PCA works? So like when we studied linear regression, we did something similar. We wanted to know like how good was our linear regression model, and in that case we used R squared, which is 1 minus the RSS over the total variance. So for PCA, it's essentially the same idea. It's 1 minus RSS over, here we have n trace q. So the only slight difference is that when we were doing regression, we had labels, and so this s squared y was was our label variance. Now we don't have any labels, we just have our data set. But if you look at the trace of Q, that's basically the sum. This is going to be the sum over, summing over J of, how do I want to write this? So it's the empirical variance of xj. So it's something very, very similar. Instead of the n times the, so this includes the n. Okay. So here it's the total label variance, and here it's the total feature variance. But it's only a small difference. But this is what we're going to use, proportion of variance. So just like with r squared, we want it to be close to 1. Okay, so we can take a look at this analytically to see what it's going to be. So n times the trace of q, well, we can just plug in our eigenvalue decomposition for q, and we can play the game where we move this around again, the v's cancel, and we have the trace of the lambda matrix. Should come back in a second. Okay. Trace of the lambda matrix, which is just the sum of the eigenvalues, the lambdas. So that's where what we put into the bottom. And then the RSS, we saw earlier in our derivation it had this form. And so here we also saw that we could split it like this. And so this trace of q again is this term. And then this last term here is we're basically projecting q, this projection matrix is going to take the first r eigenvalues. It's going to sum of the first r. So when we do sum of all of them minus the sum of the first r, we get the sum of the rest, the one starting r plus 1 to d. And so we can now plug in the RSS in here and plug in this to the denominator. And let's see, it looks like, oh yeah, okay. So, so we have the 1 we can write like this, and the minus this term is minus this. And so basically here you can see the denominator is the same, and the numerator we're taking all of them minus the last ones and what remain are the first ones. So at the end of the day, we're looking at the sum of the largest r eigenvalues over the sum of all eigenvalues. That tells us how good of a fit PCA is going to give us. And again, just like with r squared, we want this to be close to 1. As you can see, as r grows all the way to d, you definitely get 1. But as r shrinks from d, you lose a certain amount that depends on how small or how large those tail eigenvalues are, the smallest ones. They're the ones that account for the difference between numerator and denominator. Okay, so that's all the hard math stuff. Next time we're going to talk a little bit about how to compute PCA, but then we'll see some really cool examples with the faces, and you'll see how we can get better approximations of the faces as we add more and more components. And you'll see the faces kind of take shape, and yeah, I think it's kind of a cool visualization. So we'll see that on Wednesday. See you guys then.